This is a figure based on an experiment I did where I exposed some oysters to different levels of ocean acidification, and then some of them I added a secondary stressor of mechanical stress. And then I sampled their gill tissue to look at their proteomic profiles in these different conditions. And so these figures are actually based on the expression profiles of 2,677 proteins. And we can look at the effect of all these proteins at the same time in multidimensional space. So these are NMDS plots. They're kind of like PCA. And so the numbers on the axes don't mean anything, but the oysters, represented by the words on the plot, that have the most similar protein expression profiles are grouped more closely together within this multidimensional space. And so we're looking at the proteomic response of oysters to ocean acidification and mechanical stress. And so in this first plot with the pink polygons up here on the left, this is just the high versus low PCO2, so no mechanical stress is involved here. And what we see is that there is an effect of CO2 on the proteomic response, where all of the oysters exposed to the high CO2 are grouped down here, and they're clustered more closely together than the oysters at the low CO2 up here. And so the proteins that are causing this difference would be the ones that are responsible for CO2 response. If we look down here, this is just the oysters from low CO2 with the green polygons exposed to mechanical stress. And so again, there's an effect of mechanical stress on the proteome, and the oysters in the polygon at the top of the plot are the ones that were mechanically stressed. And so there's this shift in proteomic response between these two stress levels. And then with this dual stressor of high PCO2 and mechanical stress, again, here are the mechanically stressed oysters, and here are the non-stressed oysters. They were stressed only with CO2. There seems to be less of a response than we saw down here with the low CO2. See how there's more of a shift between these two groups than there is up here. And so it seems like it may be that the carbon dioxide, the high CO2 or the ocean acidification, is potentially inhibiting the oyster's ability to respond to the secondary stressor. I'll take questions.
So just so I get that right, so you see a greater difference in protein expression with mechanical stress at low PCO2 versus high PCO2.
Yes.
Right? Or could it be just that the high PCO2 effect is just potentially masking, or could that be it?
No, because these are only high CO2. So you would expect these profiles, you expect some similarity because they're all at high CO2. But my hypothesis is that the resources at the protein level are going towards the CO2 response, and so they're not responding as greatly to the mechanical stress.
Could you graph the low mechanical stress with the high mechanical stress? And how would you expect that
I could, but I have not.
That to lay out?
It's really hard to tell because this is, it's not like a real metric that these are being plotted against. So they're kind of like you can almost think of them as different scales. So I can't really compare the plots when they're different like this. But I have compared the proteins. So I can tease apart these plots and look at the proteins that are significant in terms of separating the groups out. And there is some overlap between the proteins responsible for the differences here and the differences at the high CO2. But there are proteins that are unique, and it's a minority of the proteins that are kind of that overlap response, which I'm calling the general mechanical stress response. And it was hundreds of proteins that were kind of unique to the high CO2 and mechanical stress response. So I would expect that there would be a difference between those two profiles. in a plot like this.
So have you found any interesting proteins either that are driving either the CO2 or the mechanical?
So right now, I'm having a hard time figuring out which proteins, like for example, if we look up here, which proteins are responsible for the separation along this axis, which would be like really my response between the two groups, versus the proteins responsible for separation along this axis, which would just be kind of your individual variation. I'm meeting with Julie tomorrow to talk about that, how I can figure that out. So yes, I have found interesting proteins. I can't say definitively that they are responsible for that response yet, but there are quite a few stress response proteins and some ion homeostasis and a lot of proteins related to metabolism.
Well, can you do one of those like graphs with the vectors where each data point?
I can, yeah, but the problem is that this is almost 3,000 proteins, and so there's so many proteins that are responsible for the separation of the oysters that it's like a ball. You can't see the individual vectors. You just see like this ball of arrows pointing in every single direction. So you can't do it visually like that. It'll have to be statistically somehow.
All right, very cool.